A programmable bidirectional current source circuit design is discussed in this video. The circuit is implemented with 4 operational amplifiers or op-amps and one 2.5 volt Zener diode as the initial reference voltage from an unregulated 5 volt supply. There are 2 potentiometers, one 10 kilo ohm, the other one 1 kilo ohm, that are digitally controlled potentiometer or variable resistors. The circuit is providing sourcing or sinking the output current I out to a given RL, and we want to see how this circuit is functioning and generating this current, or sourcing sinking this current, and can we find quickly a formula for this output current as a function of the setting in the circuit. Okay, so let's make the assumption that the op-amps are properly biased, so plus minus 5 or plus minus 10 volt supply voltages are, let's say, applied, and then at the same time let's consider that the output of, say, op-amp 1 and op-amp 2 and op-amp 3 are connected to negative or inverting terminal, indicating negative feedback in the for these connections or op-amps. For the fourth op-amp, we have both positive and negative feedback in the circuit, but the negative feedback is enforced dominant, and the caps of 10 picofarad 2 that are placed are just for the stabilization in the circuit, making sure that the negative feedback is dominant. So in summary, op-amps are enforced in linear region of operation. They're not saturated. As a result, we can say that op-amps benefit from virtual short, that is enforced by the negative feedback, and virtual short meaning that negative feedback forces the 2 input terminals of op-amp to have the same voltage. So for instance, this op-amp number 2, the positive terminal is grounded, 5 kilo ohm is just a matching resistor to improve the offset. So here is 0 volt via the virtual short. Because the positive and negative terminal, they have the same voltage, this is also 0 volt, so we have 0 volt here. And for the op-amp number 1, we have 2.5 volt assuming proper biasing of the Zener diode. We have 2.5 volt across the Zener diode, so this node positive terminal is 2.5 volt as a reference voltage. Virtual short would again enforce that the negative terminal of op-amp 1 is also 2.5. So across this 10 kilo ohm, we have plus minus 2.5 volt. And then op-amp number 2 is effectively, as you can see, is effectively an inverting amplifier, and therefore we have a current that has to only go this way from through the 10K and 10K. So there is, because that current cannot go or come out of the input terminal of ideal op-amp that has infinite impedance. So if we have 2.5 volt drop across this 10K, we should also have 2.5 volt drop across this 10K as well. Given that this node is 0, a drop of 2.5 from 0 indicates that the output at this node is negative 2.5. Okay, so what is the benefit of that? At this terminal of digital potentiometer, we have negative 2.5 volt. This op-amp 1 is in buffer topology or formation. As you can see, the negative terminal is connected to the output of the op-amp. So 2.5 volt on negative terminal appears at the output as well. So this digital 10K potentiometer, on one side it has 2.5 volt, on the other side it has negative 2.5 volt as we wanted. Now I'm going to talk about the biasing of this Zener diode quickly. So after that, I'm going to cover the impact of this digitally controlled potentiometer or variable resistor in terms of defining a voltage here, and then at that point I am going to find the I out as a function of the voltage V here, so that we get the formula we want. Quickly here, we have a 2.5 Zener diode and the 390 ohm via the connection between the 5 volt and Zener diode just provides the bias current for the Zener diode, so IZ. Of course, this IZ is as simple as the voltage drop across 390, which is 5 minus 2.5 volt, and then divide by the 390 ohm, which is then roughly 6.4 milliamp, which is good enough practically to make sure that this Zener diode has enough ample current to be outside of the knee, let's say, region of the IV curve. So it's stable 2.5. There are many providers. When you search Mauser or other providers, you will find many Zener diodes. One example is from Vishay. So 1N5222 is a Zener diode of 2.5 volt with nominal current between 0.25 milliamp to 20 milliamp. Also, Microsemi provides some, but basically this one is just good enough for our purpose, 1N5222. Okay, so we now have the Zener diode properly biased with enough current, 6.4 milliamp. So we can now assume 2.5 and negative 2.5 on the two sides of this digital potentiometer stable. Now, what is the meaning of this digital potentiometer? As an example, again, microchip analog devices, all of them and many other have their own implementation of the digital potentiometer, but here is one good example. So analog devices has 1 channel, 2 channel, and 4 channel versions of, let's say, I'm going to shift it up so that it's easily observable. All right, so the AD 8400 or 8400 is 1 channel, AD 8402 is 2 channel, and AD 843 is 4 channel. You can see that 1, 2, 3, 4. Basically, it means there are 4 digitally controlled independent potentiometers. For example, if I need a 10 kilo ohm digital potentiometer here and a 1 kilo ohm digital potentiometer here, I can use 2 of these channels and control them independently. Control word is 256 position. Basically, the control word for this one is just D1 equal to a value between 0, an integer value between 0 and 255, so 256. And also the control word for the second potentiometer is again a value between 0 and 255 because it is 8-bit digital code word. And then we can implement either a 1 kilo ohm let's say potentiometer, a 10 kilo ohm, or even 50k or 100k. So there are 4 different possible total value for the resistor. In this case, we need a 1K and 10K. So we can set one channel in 1K and another channel in 10K mode. There are many other options available. For example, another one from Analog Device is another 8-bit 2-channel, not 4, 805232 potentiometer. This one is only able to do 10K, 50K, and 100K. So 1K is not there. So it's not the perfect choice for this example, but it is there as another example. Okay, so with that in mind, let me just make the assumption that we are using, let's say, AD8402 or let's say 03 for the sake of in this example. So with that in mind, I'm going to just put this aside, and let me go to computing how this potentiometer is working and what is the voltage at the positive input terminal of op-amp 3. Op-amp 3 is in buffer mode. So again, because of virtual short, whatever V appears at the positive terminal is enforced to be at negative, and therefore V at the buffer is at the output. So what is the value of this V which appears at the input of the final stage? Okay, so this V is as simple as this. I have V equal to so what happens is, via this connection, when the digital code word for this potentiometer is at, let's say, 0, this pointer is just connected to the lowest point, which means output V becomes equal to negative 2.5 volt. When the code word, digital code word for this potentiometer is 255, then this pointer is connected to here, which means the highest voltage, and then therefore V is almost 2.5 volt. So and this happens linearly depending on the value of the code word D that moves between 0 and 255. We can program it ourselves. So I can say this voltage V, which is this voltage V, is equal to the lowest value, negative 2.5, and then plus the delta 5 times number of steps. So steps being the code word divided by the 256. So basically what happens, we get 2.5 volt times and then we get D1 over 128 minus 1. As you can see, when in this formula, when D1 is 0, we get 2.5. We get negative 2.5 volts because there's a negative 1. And when D1 is 255, we get roughly plus 2.5, exactly as we expect. So let's refer to this as equation 1. Basically the equation that defines the voltage V as a function of the code word D1 for this potentiometer. Okay, so let's move on to the next computation we need. In this, voltage V appears at the input of the last stage. Let's refer to the voltage at the positive terminal and also the voltage at negative terminal, which should be the same because of the virtual short for the final op-amp. Let's refer to as Vx. So we have Vx or at the positive and negative terminals. We can neglect cap because, as I said, for our analysis, the caps are not important. Those are for only stabilizing and making sure that the negative feedback is dominant in the circuit, just stabilizing the last op-amp because it has both positive and negative feedback. Now, it's actually just the voltage division between R1 and R2 to get to the output of this op-amp. So V4 is simply a voltage division, V4 and Vx, just basically voltage division between R2 and R1. So I can say V4, let me just write it here. So V4 is equal to, I'm going to write it here. V4 is equal to, so it would be a scale up, R2 plus R1 divided by R1 times Vx. Basically, Vx divided by R1 becomes this current, and then this current has to go through the series of R2, R1. So V4 is this current times R2 plus R1, and that's exactly what I did. Vx divided by R1 is the current, and then times R2 plus R1. So in summary, I get V4 is equal to 1 plus R2 over R1 times Vx. Let's refer to this as equation number 2. Okay, so let's also consider defining V4 via this route. So what I can say, I observe that there is the output current I out, and also there is another current in, let's say, blue, like this, that is coming from V. So I can find V4 given these currents and the amount of voltage drop they cause. I can write effectively a KVL, or Kirchhoff voltage law, which is the sum of voltage drops basically. So I can say, using KVL or Kirchhoff voltage law, which is one of the circuit laws, I can say V4 is the voltage drop across RA. So it's going to be RA times, there are two currents that are going through RA, I out and the blue current. So let's refer to the blue current as IR1. So I'm going to write RA I out plus IR1. Okay, so that's only voltage drop across this guy. I also need to take into account the voltage drop across these two resistors, RB and R1, and the only thing going through them is IR1, because again, nothing can go or come out of the positive input terminal of ideal op-amp because it has effectively infinite impedance. So these two resistors are effectively in series. Therefore, I can say plus let's say plus RB plus R1 in series times IR1. Now we get to the voltage V here, so I have to add that voltage V as well. Basically, I am saying V plus this voltage drop, delta V, plus this voltage drop, delta V, gets us to V4. That's exactly what we are doing. Okay, so let's just simplify a little bit. The only thing I can say is I can also compute IR1 quickly. So let's refer to this as, so this was equation 2. Let's refer to this as equation 3 here. So this one is equation 3. And then let's write the equation for, let's say, IR1. So IR1 R1, this current, blue current, is equal to voltage drop across R1 divided by the value of R1. So VR1 divided by R1. But VR1 is just simply Vx minus V, the two voltages across R1. So Vx minus V divided by R1. Okay, so I'm going to keep this as my equation number. So let me just write it in a better way. It's Vx minus V divided by R1. So this is my equation number 4. I'm going to apply equation number 4 in 3, and then I'm going to set 3 to 2 because both 3 and 2 are trying to find V or define V4 as a function of a bunch of things. So I'm going to say using 3 and 4 and then using 2 as well, which I'm going to use to substitute IR1, I can say, maybe I just put it here so that things are in a better fashion. Let me write it here. I can say using 2, 3, 4, I have 1 plus R2 over R1 times Vx, which is this guy, basically V4, equal to now this guy, which is RA I out. Now we have IR1. So what I'm going to do is I'm going to just factor out and write it once. So let me do it this way. Factor IR1 and write RA plus RB plus R1. So I took care of this guy and this guy times IR1, and then finally we have plus V. But then substitute for IR1 using equation 4. So I get 1 plus, and instead of, I'm going to talk about it, R2 over R1 Vx RA I out plus Vx minus V divided by R1, which I'm going to shift it below the numerator of RA plus RB over R1 plus 1 plus V. Now we have now the benefit of having this accurate digital potentiometer comes into picture. So it's a 1 kilo ohm that we can control accurately with the steps of 256. So I'm going to write it here. For the 1 kilo ohm digitally controlled potentiometer is digitally controlled with the steps of 0 to 255, so 8 bits basically. Control word D2. And as a result, the value can be with the steps of 1 kilo ohm divided by, so step of 256, which is roughly 3.9 ohm. So all I'm saying is this resistor 1 kilo ohm here, we can digitally control it via 256 steps with values of 3.9 ohm increment. So the benefit of that is I can set accurately RA plus RB equal to roughly R2 equal to 1 kilo ohm. And R2 is this resistor 1 kilo ohm. So in this example, if RA is 20 ohm, I can set accurately RB to 980. So as I'm saying, this one is 20 ohm here, small resistor. This one is the one that we can control. So 1 kilo ohm potentiometer RB, and therefore this is the one I'm going to set 980 roughly. So therefore I can set the value of them to be equal to R2 to be 1K. This is equation number 5. So this R2 here, I'm gonna just highlight it. This R2 here is the one that I'm gonna use equation 5. So I'm gonna say using equation 5, it's 1 plus basically RA plus RB divided by R1 times Vx is equal to RA I out, this one, and then plus Vx here times 1 plus RA plus RB divided by R1, and then minus V plus V cancel out, and then we have minus V times this guy. So minus RA plus RB divided by R1 times V. Okay, so the nice thing about this whole thing is, as you can see, these two cancel out each other as long as we can satisfy this with the accurate digital potentiometer, and therefore the circuit just resulting, this computation resulting RA out is equal to RA plus RB divided by R1 times V. And the V is the voltage that is at the output of op-amp 3, which is controlled by the first digital potentiometer. So in summary, what I can say, the I out current is equal to, with a good accuracy, is equal to RA plus RB divided by RA times V over R1. And R1 is 50 kilo ohm. So keep in mind that the values like R2 is 1K, RA is a small resistor, 20 ohm, or can be as low as 10 ohm. This is a 1K potentiometer that we digitally control to 980, so that the sum of RA plus RB is equal to R2 1K. R1 is repeated here as is here, so we have 50K and we have 50K here as well. So in this case, if for instance we just substitute values, this one is just 1K, this one is 20 ohm, this one is 50K, and this over 50K divided by 20 ohm is just simply 1,000s. So this is my formula, and the specific case is indicating 0.001 V and in this design, and V as controlled here is a value from equation 1 between 2.5 and negative 2.5. So if you want to let's say, let me shift it here so that things are in better shape. I'm going to shift this whole thing here, and I'm going to just write it here. And if we substitute, say, from equation number 1, this equation, we have effectively 0.001 times 2.5, which means 2.5 milliamp. So 2.5 milliamp, because this is effectively just, as you can see, in the form of Siemens, so that is ohm inverse, and we have 2.5 milliamp times the code word D1, so D1 over 228 minus 1. So basically what it means, we are able to control the output current in the range of plus 2.5 milliamp and minus 2.5 milliamp using the 256 step code word for this potentiometer, and the second code word D2 is only for this RB to be set accurate as close as possible to 980 or whatever needed, so that the sum of RA and RB is close to 1 kilo ohm, as close as possible. So basically satisfying number 5 is achieved by the D2 control word for the 1 kilo ohm potentiometer. I hope that this example is helpful to show how we can design a programmable bidirectional current source using digital potentiometer and also a Zener diode and a combination of operational amplifiers. Thanks for watching.